Hello everybody, this is Mostapha Kalami Heris from Yarpiz and I'm going to talk about inner product. Inner product is a simple yet powerful tool in mathematics, physics and machine learning. It has enormous applications in different fields of science and engineering, and it has many applications in machine learning especially. And in this video, I'm going to talk about its mathematical definition and theoretical background, and also I'll give you some examples of its applications. And those applications include PCA, that's a dimensionality reduction algorithm, and recommendation systems, search engines, signal processing, and quantum mechanics. Inner product is actually a very simple operation between two vectors, and sometimes we call it dot product. You can use that name as well, and that actually quantifies the similarity between two vectors. It is really simple. Assume that you have two vectors a and b, and they have the same size and they have n elements, and you just multiply the first element of two vectors, second element of two vectors, and then add up all of these product terms, and that's here. And this one is actually the multiplication or product of the first elements of two vectors, and this is the second element, and these are the nth elements of the vectors a and b. And we add all them together to get the inner product or dot product of two vectors. It is really simple, but it is very powerful. And the main purpose is to quantify or measure the similarity between two vectors. Okay, for example, if we have these two vectors, then how we can calculate the inner product of these two vectors. It is simple. You simply multiply 2 by 4, 3 by 1, and negative 1 by 5, and that's 2 by 4, it's 8. 3 by 1, it is 3, and negative 1 by 5, it's negative 5, and the result is 8 plus 3 minus 5, and that becomes 6. You see, whenever the signs are same, then the result is positive. When the signs are not same, the result is negative, and that reduces the total sum. But when the signs are agree, then they increase the sum, and that's the point. Actually, the defining the inner product in this term, it actually has the meaning of similarity, because when the components of two vectors are in the same direction, they have the same sign, then they are amplifying the total sum. If they are in opposite directions, then they are reducing the total sum, and that's actually the way we define the inner product. Okay, the inner product actually can be defined using the projection. Assume that we have two vectors a and b, and one way to compute the inner product between these two vectors is to just draw a line like this, and which is perpendicular to the vector a, and find the projection of vector b on vector a, and that's a size, and this is a number. And if we multiply this number by the length of vector A, that's the inner product. And we know that this is given by the length of vector B times cosine of this angle theta. And the total result is this. And this is the length of projection. And if we multiply this by the length of vector A, then we will get the inner product, and that's defined in this way. B times cosine theta is actually the projection of B on vector A, and we multiply A by that projection to get the inner product. And it is also the same if you, for example, find the projection of vector A on B. It is the same. You can actually find this projection as well. This is going to be the projection of vector A on B. It is the same, and the result would be the same if you calculate it. We have another way to compute the inner product. Assume the same vectors A and B. We have these two vectors, and let's decompose these vectors into x and y components, in horizontal and vertical components. And ax and ay, they are both vectors, and we know that a is the sum of these two vectors, and it's the same for b. So we decompose both of vectors into horizontal and vertical components. Now, we want to calculate a dot product b. And we know that a is ax plus ay, and b is bx plus by. And we can expand this term. And actually we have four terms. One, ax times bx, ay times by, and also a x times by and ay times by. And we have four terms, and these are those four terms: ax times bx, and ay times bx, ax times by, and ay times by. But we know that these are perpendicular and they don't have any projection on each other, so these are just simple zeros, and we can ignore these terms. And what we have is just the product of two horizontal components, ax and bx, and two vertical components, ay and by. And if we use these, then we get the same formula we had. We actually multiply two x components and then add the multiplication of two y components to get it. However, here ax and bx actually are vectors, but we know that because they are parallel to each other, the dot product is simply the multiplication of their size, so it's the same. Okay, that's actually why we compute the dot product or inner product in this way, that we multiply ith element of two vectors and then add them together. The inner product actually can have a positive, 0, or negative value. If it is positive, then the vectors are aligned or they are in similar directions. If the value is negative, then these are in opposite directions. And if it is 0, then they are simply perpendicular. They are orthogonal to each other. For example, let's assume that this vector is simply love. Love is in emotion, and the opposite of that is hate. It is on opposite direction. And if we calculate the inner product between love and hate, it must be a negative number. Okay, we can. These days we have several algorithms that can model concepts and words in terms of numbers and vectors in a vector space. If we have a numerical representation of these concepts, love and hate, and if we can multiply them using the inner product, it will be definitely a negative number because they are pointing to the opposite direction. However, if you remove the concept of love, you don't get the hatred. It's not actually lack of love does not mean necessarily the hate. It is indifference. It is the neutral emotion. And that's the vector which is perpendicular, which is orthogonal to both of these. And we know that L times I, that's the dot product or inner product, it is 0. And also H times I, that's also 0. And actually, this is a good example of the relationship between words and vectors. Uh, yes, the opposite direction of love is hate, and their inner product is a negative number. But if you want to remove love, then you must be indifferent. And it doesn't mean that removing love can lead to hatred. Okay, and we have also another similarity metric which is known as cosine similarity, and it is simply the cosine between two the cosine of the angle between two vectors. If we have A and B here, this one actually is defined as cosine of theta. This is the cosine similarity. But we know that the dot product, this one, is simply the size of A times size of B times cosine of theta. And if we divide it by A times B, we can remove these as well. If we divide it, then these two cancel each other out, and these also cancel. And cosine similarity is simply the value of cosine between cosine of the angle between two vectors, and the range is between -1 and 1. It is actually a normalized version of the inner product. And if two vectors are perfectly aligned, then the angle between them is 0. And yeah, that's the maximum value for cosine similarity. And then we have 1 as the value of cosine similarity. And the minimum value is -1. That's exactly opposite direction. And 0 is for orthogonal or perpendicular vectors. That's related to the inner product. And we can use inner product in recommender systems. Assume that you have a website which sells some products or have some movies or shows, and you want to recommend a new item to the customer, to the user. Then, based on the model, based on the data that you have from the user, you need to predict the value of the score or rating of a user to a specific item, say a movie. Then one way to estimate that value, that score, is to simply calculate the inner product between two vectors. And one vector is U, the user vector, that's the user preference. For example, you can model the user preferences for different kinds of products or different genres of the movies. And also, you can model each item in your website or in your system using the same set of features. So you have some features and you need to express the users and the items in the same space. And in that space, inner product will tell you that how similar the preference of the user is to an item. And that's the key. Here we have a score that's actually an estimate rating or an estimate score of the user to a new item and that's simply an inner product. And U actually contains the values of features like genre, category, anything related to the item, and we have those attributes for the item as well. And we have all of these data. And for example, let's assume that we have just 4 genres in our database: comedy, action, drama, and horror. And this user is really interested in comedy movies and somehow interested in action. These are positive, but uh, they are not interested in horror movies. So it's because of the negative weight we have, because of the negative value. Now we have an item, a movie, which is expressed in the same space and using a different, using a set of numbers. Okay, here we actually is a comedy movie, and somehow it contains some action, some drama, very little, but doesn't contain any horror. Opposite of that, it's negative. It lacks any horror components. Okay, and because of that, if you compute actually these products, okay, you will get 1. And you see here, because we have two negative numbers, it increases this score. Okay, and this is actually a high value of a score, and it can predict that the user is highly likely to enjoy this movie. Okay, that's actually an example of how an inner product works. Assume the same user, but a different item in the database. This one is actually not a comedy at all. It has some action. It doesn't have any component drama, and actually it lacks those components. And also it is a horror movie. Okay, and because of that, we have a positive weight here, we have negative weight here, and because of that, and because of the mismatch here, you see these two items. User likes comedy movie, but this one doesn't have any comedy component, and because of that, we end up with this negative score. And because of that, the user is unlikely to enjoy this movie at all. So we're not going to recommend this movie because we know that it's not the user's most favorite one. So that's a good way to build a recommendation system, and some basic recommendation systems use that in early days, but still there are some complicated structures which use the same strategy but with modifications, with improvements. But at the heart of that, we have the inner product, because it is super fast, it is very effective, and very good at estimating the similarity between two vectors. Also, we have another algorithm known as principal component analysis, PCA, which is actually used to remove some dimensions from data. It's actually a dimensionality reduction algorithm. Assume that we have a data set in n-dimensional space, say for example 10-dimensional space. Sometimes it happens that we can come up with a lower with a new representation of the data in lower dimensional space, for example in 2-dimensional or 3-dimensional space. And the way we do this is actually we need to center the data, and we calculate the covariance of that, and using this covariance matrix we can find the directions which maximizes the variance, and based on this we can create new features, and we can reduce the number of features. And how we are doing this? Actually, here X is our data set, and we have m rows. So these are m rows, and these are actually our data points, and we have n columns. Okay, and the columns, actually each column is related to one feature, and each row is related to one data point in our database. Okay, if we reduce the subtractive value of mean which is represented by letter mu here, we actually center the data around the mean value of all of the features. And if we want to calculate the covariance matrix of this centered matrix, then we can do it in this way. However, here we actually had the n features, and transpose of that will be n features in this way, because when transposing a matrix, actually you're switching the rows and columns. And we know that when we're calculating the product of two matrices, we multiply rows of the first matrix by the columns of the second matrix. And that's same as the inner product. Actually, when we're calculating this one, each component of this covariance matrix is actually the inner product between feature I and feature J. And that's the similarity between two features. Okay, and in this way, we get a matrix which measures the similarities between two vectors. And based on that, we can actually find the similar features and group them together and remove some redundant information from the data set. And that helps us. That's the heart of the PCA algorithm. But actually, it is complicated. We need more mathematics to show that. But you see here, in this formula of the calculating the covariance of the data set, which is centered around the mean value, we are actually measuring the similarity between two features. And we need that because we need to find similar features and then mix them together or remove some redundant information from the data set. And that's the main thing with the PCA. Also, we have a mechanism in neural networks and machine learning known as attention mechanism. And that's the mechanism that's powering up our generative models, large language models, and we use that. And when we want to calculate the similarity between the user query and the key vector, then we need to generate actually the attention weights. And we have many attention methods, but these are some of them: dot product attention, or scale dot product attention, or multi-head attention. All of them actually, they use dot product as the fundamental component to calculate the similarity between the query and key vectors. That's it. That's the very advanced application of the inner product. And these days you use all of these models, especially when you're using the large language models, and I'm sure that you're using those. And when you're searching for something in database, or you're using Google, for example, to search, some form of inner product or cosine similarity is actually being used while using for the documents in the data set. It actually, a search engine uses the similarity metrics like inner product or cosine to find the similar documents to the user queries. The vector stores or vector databases these days, which are at the heart of the technologies like RAG, retrieval augmented generation, which are actually a layer on top of the large language models. These vector stores or vector databases use some form of similarity metrics, and because of its simplicity and it is speed, inner product is usually used. Sometimes, yes, it is modified, it is combined with other similarity metrics or cosine similarity as well, but it is very useful and it is the base for so many similarity metrics. So we have the inner product in information retrieval, and we can find so many applications of these in vector databases and search engines as well. However, sometimes actually we can generalize the concept of inner product to other fields, to other spaces, and one of them is actually the space of the domain of functions. Assume that we have these vectors, and assume that these values, AIs, actually are the values of two functions at specific times, or for specific values of arguments here. Okay, so this is AI actually is the samples of some function, and it's the same for BI. BIs are actually the samples of some functions. If we get more samples, say infinite samples, then actually we can convert this summation to this integral. And instead of having discrete values, we have continuous values. And here it is actually the continuous inner product, and that's the inner product defined for functions. It is very useful. So for two functions ft and gt, we can define the inner product in this term, and that's the integral for f of t and g of t between two ranges. Sometimes it can be between negative infinity and positive infinity, but sometimes it can be just focused on a predefined interval. We have many applications in transforms like Fourier series, Fourier transform, and Laplace transform, wavelet, Hilbert transform. All of them actually, they use this kind of inner product. But how? Actually, it has the same set of features, same set of properties. For example, symmetry. Dot product of a and b, a times b equals to b times a, and also it's the same for two functions. It is a linear operator, so if you have a constant here, c, it goes out of the product. It's the same for functions. Also, it is always positive definite. Dot product of a by itself, it's always a non-negative value, and dot product of any function to itself is always a non-negative value, and we know that because it's a positive number actually always, or actually non-negative number. Now assume that we have a Fourier series. It's actually a theory is that you can express any given periodic function in terms of summations of a constant term and infinite cosine and sines. And those cosines and sines actually they have a basic frequency. Actually it is this is here. You have a basic frequency, and you have multiplies of that frequency in your cosines and sines. And this one is also is cosine with zero frequency. It's a constant term. Sometimes it is called DC component, and it's a constant number. And these numbers a0 or a0, an, bn, these are coefficients, and these are Euler's formulas to compute these coefficients. And they are actually inner products. Here, you see, we multiply f of t by cosine. If we want to actually find the value of a of n, we calculate the similarity between f of t and cosine of this quantity here, 2 pi nt divided by t, and t the capital T is the period of the this periodic function. Okay, and it is same for this one as well. We calculate the similarity between f of t and this sign to get the value of b of n, bn. Okay, and here actually we are calculating the similarity of f of t and just a constant number 1, and it is known as the average value of the function, but taking an average is actually kind of calculating the similarity between a function or a vector to a constant number. Here we have this same logic. So in order to find these coefficients, all of them, you see here, this one, this one, this one, for all of them, we calculate the inner product of f of t with some function, and that function presents in the Fourier series of the original function. Okay, so if you want to find the coefficient of this function, cosine, then you calculate the similarity between f of t to that function. Okay, and that's the number here. And an, bn, or a0, that's the contribution of the basic functions in the function ft. So that's simply an inner product. And an, actually the number shows that how similar f of t is to cosine of 2 pi n t divided by capital T. And bn is the same. It measures the similarity between f of t and that sine term. It is the same for Fourier transform. That's an extension for the Fourier series for actually non-periodic functions, and it includes all of the possible frequencies, but it analyzes the functions which are only have the oscillation behavior. Here we have this function, and actually at each frequency omega we measure the similarity between the function, the original function in time domain, to that kernel function. We call this kernel function. It is the same for Laplace transform as well. These are both kernel functions or basic functions. We actually calculate the similarity of f of t to any of these, and we get another function of omega or s, and that actually says that what's the contribution of this frequency component in the time domain function f of t, and we can decompose actually the function in terms of its fundamental frequencies. But for Fourier transform, it only considers the oscillation components, but for Laplace transform, oscillation and decay or growth are also considered. But the logic is the same. For the wavelets, for the Hilbert transform, for so many other transforms in mathematics, it's the same. Actually, we calculate the similarity, and that's the inner product, but it is the continuous version of the inner product. And also in quantum mechanics, we have inner product. That's bracket notation, and it actually, this notation here, it is the bracket notation between two quantum states, psi and phi, and that's called the overlap. And two states, psi and phi, the overlap of them is represented by this, and that's simply a inner product. And the transition probability from psi to phi, or vice versa, it is given by this formula, and that's actually that says that transition probability from psi to phi or phi to psi is represented by square of the magnitude of their inner product, because usually psi and phi, they are complex numbers. We need to get this actually magnitude to make sure that it is going to be a real number. But here, a high value for overlap or inner product means that these two states are more similar and they have higher transition probability. And that's another application of inner product. I hope this video was helpful, and if you find it helpful, please let me know, and hit the like button if you liked it, hit the subscribe button, and introduce the video or channel to your friends. And thank you for watching, and if you have any comments, feedbacks, questions, please let me know in the comment section. And thank you again for watching, and wish you all the best.